Hello, Lucia. How are you? Welcome to the stream. Today we're going to be doing the Biweekly contest 137. I just share the link and let's get started. Let me see. All right, so let's start with problem 1. Let me share the link. Question 1. So yeah, this contest is a little odd because even Q1 is a medium, and actually, and they are both. They are part 1 and part 2, and then part 1 and part 2, and they are exactly the same problems, but with different constraints. So that means that if you know that you can solve them all, it would be better to go for part 2 directly and solve that, and then use your solution for part 1. Didn't participate in this one, so this will all be all learning. That's awesome. Okay, so let's start. So I'm not gonna do the strategy that I'm recommending during the contest. I'm gonna go in order, and I'm gonna do the simpler, the more brute force solution first, and then the optimize. But remember that in the contest you would just do the efficient solution and then reuse that. And so, well, the Q1 is called find the power of k-size subarrays, part 1. And you're given an array of integers nums of length n and a positive integer k. The power of an array is defined as its maximum element if all of its elements are consecutive and sorted in ascending order, or -1 otherwise. Right? So it's kind of, so you have to think about it a little bit to actually get it. So you need to find the power of all subarrays of size k. Right? Here there's a fixed size. And so you have to return an integer array results of size n minus k plus 1, where results of I is the power of nums of, well, anyway, so here we have example 1, where, so here the first output is 3, which, well, the size of the window is 3, right? So here we are considering this 3, and they are, we can call this like a stair, I guess, in car games, like 1, 2, 3. And so they are in ascending order, and each element is the one before plus 1. And so this is true, and so the value is the value of the last one, right? So it's 3. Then you shift the window 1 to the right, and you have 2, 3, 4, which is also a stair. And so the value is 4. But now, when you shift it 1 more, then it's not a stair anymore. It's like a peak. It's like a peak. And so it's -1. And then here it's like a stair, but it goes down. It's decreasing. You can't hear me? Oh. Audio is fine. Maybe John? Oh, you scare me for a moment. I thought I was... Can you confirm? Can you fix it on your side? By the way, welcome, maybe John. So Lucia, could you, were you able to fix it? All right, so I was just going over the example just to make sure that we understand the problem. But now I'm waiting for you to... Oh, who knows what happened? Yeah, just restart is the solution to all the problems, to all the computer problems. All right, so... Okay, so this is Q1, so the constraints are not so bad. It's up to 500 elements, numbers. And so we could do something quadratic, like we could just do this like this, right? We can go over the elements, right? So this is this is the number of elements. Well, I guess we could just do a list comprehension probably. So we want to check if it is a stair, which means that from 1 to k, so if this is true for all of them, then we want nums of I plus j minus 1, which is the maximum value of that window. And here we want so we want nums of I plus j minus 1 plus 1 equals nums of I plus j, right? So that means that for every number, the previous one plus 1 equals the current value. And so this is an all and else minus 1. So that's a long line, but I think it is correct. Maybe there's some parentheses missing. No, it seems it is good. All right, so it works. So yeah, there's not much to say about this one. So maybe we can move on to question 2. Okay, so like I said, this is the same problem, but now the size is up to 10 to the 5th, right? So we cannot do something quadratic. So what we can do, so notice that here every time we shift, we move the window 1 to the right. But notice that we're just adding one element to the right. So whatever we checked, when we checked if it was a stair, and we found, for example, we found that it was not a stair, that we found that at some point the element did not satisfy this condition, there was an element, then we can remember the last one that did not satisfy, right? And so if we already know which one was the last, then we can just check the element that we're adding, and that should be enough. So let's say that we keep track of where we are starting the current streak. Okay, so let's say that initially we don't have any group, any streak, and we're gonna go over the elements. So now we want to know if we have, so we're processing nums of I, and we want to see if we have to start a new streak from nums of I, right? If we cannot add it to the previous element, then we have to start a new group, right? And we're gonna keep track of that. So there's a special case where I is 0. In that case, we have to start a group from here. We have to, or if nums of I minus 1 plus 1 is different than nums of I, then in that case, nums of I has to starts a new group, right? So we keep track of that, and now we want to know if we have a complete window, right? So the first element of our window is going to be I minus k plus 1, right? And if that is greater than or equal to 0, that means that we are the window that ends at I is already a complete window, and that means that we need to append something to the result, and we either append nums of I or minus 1, right? And nums of I is going to be if, remember, this is our first element in the window, the leftmost element of the window, and we want to know if that is greater than or equal to the start of this group, right? Because that means that that we have a group, the longest group includes our window. If the group is shorter than the window, it means that we cannot cover the whole window with a stair. And so that is going to be our solution. And seems to work with the examples at least, and it passes. Cool. 1.3 seconds, that's a lot. Not sure why. This is pretty efficient. Maybe there are a lot of test cases. Makes sense. Yeah, this is kind of it's a sliding window, but with fixed size, and yes, and we need to keep track of this, of where we're starting the longest streak, that is a stair. All right. So yeah, so here let me share the solution, and let's go to, so Q3 and Q4 are both hearts, right? So that's not usual, I think. All right, so yeah, I like this problem. It has a short description. So the maximum value sum by placing 3 rooks. Part 1, you are given M by N 2D array board representing a chessboard where board of I, J represents the value of the cell I, comma J. Rooks in the same row or column attack each other. You need to place 3 rooks on the chessboard such that the rooks do not attack each other. Return the maximum sum of the cell values on which the rooks are placed. Okay, and here we have an example. Example 1. So here they draw it for us. And so it seems like, so there are many negatives which don't seem to be good. So and here there's a 2. Maybe we can use the 2, right? That would be good. So if we placed 1 here, well, okay, I mean, here it is. Well, maybe we can ignore it for a moment, but yeah, my intuition would be to go for the 2 and then try 2 1s. That's obviously going to be the maximum, and we can do it because we can choose this 2, this one here, and this one here, and this 2. So the answer is 4. That makes sense. And then, well, here this is pretty obvious because you only have 1s, so the answer is obviously going to be 3. And yeah, notice that of course we have it's at least 3 by 3, so the rows and the columns are at least 3. All right, so and yeah, and the constraints are important here. The dimensions are up to 100. So what does this mean? So one, like a brute force idea would be to just try all the possibilities, and that would give us roughly like for each dimension we have 100 possibilities in the worst case, right? And we have 6 dimensions, like 2 for each rook, and so this would be 100 to the 6, which is 10 to the 12, right? So this is too much, right? So we have to be smarter than that. So what can we do? So one observation that we can have is, so let's say, sorry that this is not looking good, but so let's say that we have selected 3 rows, right? So they have to be distinct, right? They cannot be in the same row. Yeah, this is messy, but that's fine. So notice that on each row there will be, let's say that these 3 values. Let's say that these are the 3 top values in this row, in row 1. What I claim is that I only need to consider these 3 values. If I only consider these 3 values, I'm gonna find the optimal for these rows, right? And why is that? Well, let's say that I didn't. Let's say that I chose one value. Let's say that I chose this value here. Well, notice that I can make a change. I can exchange this choice, and let's say that, and one of the red values are going to be available, right? Because the only ones that are not that might not be available are the ones of the that are on the same column as the other 2 rooks, right? So let's say that maybe this is not available because it's in the same column as this one, and maybe this is not available because it's in the same column as this one, but this one is available. So we can exchange. We can make an exchange here, and since the red ones were the biggest ones, by making this exchange, we improve our solution, and that means that this solution was not optimal in the first place, and so that's a contradiction. So so that means that we can just consider those 3 for each. And so with that, we already have a solution, right? Because so that means that instead of having 10 to the 100 to the 6, we're gonna have the choice of the 3 rows, which is 100 to the 3rd, and then we have 3 choices for each of the rows, right? In each row we have 3 potential columns, right? And so this is 3 to 3, and so this is going to be 10 to the 6 times 27. So this is 27 million, which is good. It's not a lot. And so how do we do this? All right, it's much less. Yes. So how do we do it? Well, we first calculate the let's call it the max columns, and yeah, so for each row I'm gonna have so there's this n-largest function in Python, which is part of the heap queue module. So we want the 3 largest, and we want to know the index of the column, right? Because since the columns cannot be the same, then we need to know we need to know the column, not just the value, right? So that we can then check if they are different. And so here I'm gonna pass all the possible columns, and then I'm gonna use as the comparison, I'm gonna use the board value, right? So that's gonna give me, and I think this returns an iterable, but I'm gonna be accessing it more than once. So I'm gonna create a list. And so now we can just do all our, we're gonna have like 6 loops, 6 nested loops, right? Because, okay, so this is going to be our maximum, which can be negative, right? So we have to initialize it with minus infinity. And so we want row 1, then row 2 is gonna be like this, and then row 3. And now we want col1 to be in the max columns of row 1, right? And then col2 is going to be in the max columns of row 2, but here we want C1 to be different than C2, right? If C2 is the same, then we don't want that. They'll be attacking in that case. And finally C3 in here, and again C3 has to be different than the 2 previous ones. Okay, so now we found a solution. So now we just get the maximum. So yeah, this one is not a big deal. I mean, you need the observation that you only need to consider 3 values for each row. I mean, yeah. Cool. All right, so let's go to Q4. Yeah, and the nesting is not that bad. Yeah. Yeah, I mean, you could use continue here to avoid having more levels of indentation. Wait. All right, so here, what can we do? So this solution, the solution of Q4 is based on the same idea, but we want to save. So, well, let me first tell you what the constraints are. Instead of 100, they now go up to 500, right? So that means that our solution is not gonna work, but maybe we can. So notice that the sizes are larger, but they're not crazy large, right? They're a bit larger. So it's 5 each dimension, so 25 in total. But so notice that if we remove 1 from here, so if we had like something like this, then that would be good enough, right? So because this is 25 and 9. So it's within the limits of what we can do. So so notice that if we had that hints at a solution that would be where we would be choosing 2 columns, right? 2 rows. So let's say that we have 1 row here that we're selecting and 1 row here. And let's say that our other row is going to be somewhere here, right? So let's say this is row 1, this is row 2, and this is row 3. And so, and let's say that we know that, well, here's the column. So here's where we place and let's say here there's another the other rook, right? So so that means that we cannot select the elements that are here or here in this column, right? But that means that we want to choose the maximum value in these 3 regions, right? So maybe we can use some data structure to do this quickly, right? So there's so this looks like we could use some range queries, right? So if we could make a query for this range, and then a query for this range, and then a query for this range, like a max query, then that would give us our solution, right? But for that we could use a segment tree that gives us range queries of the maximum value. But the problem here is that we have many rows, right? But maybe we can create a segment tree such that every time we move R2, every time we add a row to this region, we take the maximum of the whole column in this region, right? So here if we have 3, 1, and 2, we're gonna keep track of the maximum of each column, right? So here is column 1, and the maximum is 3, right? So here we have a 3, and maybe here we have 7, 6, and 2. So here we will have a 7. So notice how we can have just one array which has the maximum of each column in the region, in the rows in this region. And then since we're gonna use a segment tree, we can make these queries, these ranger queries, and it's gonna give us effectively the maximum of each region. Okay, so that is the idea. So I'm gonna use the a segment tree just as a black box Remember, I always tell you that you should have one, even if you are not an advanced LeetCoder. So even if you don't know the internals of the segment tree, just copy one implementation, learn the interface, like learn how to use it, and use it to solve problems, right? So you don't need to know the internals, just like you don't know the internals of a dictionary maybe, or a sorted list. The approach is clear. Cool. So yeah, we're gonna use some things from the not sure so much how we'll use the segment tree, but let's see. What do you mean? So we're gonna construct this segment tree that I have here, right? That is gonna have, we're gonna keep adding. So this region, the R1 region, it's gonna grow, right? When we move R2, this region, we're gonna add a new row to this region, and that means that we're gonna update. Hey, say Yad, welcome. That means that we're gonna update the maximum in each column, right? Like I shown here, we're gonna keep track only one segment tree. Remember that the segment tree is just an array. It's just an array that has this quick range queries, right? So then if we know these values, right, where we're placing the in which columns we're placing the rooks, the other two rooks, then we know we're gonna have, so maybe this one is not allowed and maybe this one is not allowed. We're gonna have two elements that are not allowed. So then we're gonna make we're gonna ask what is the max in this range, what is the max in this range, and what is the max in this range. We're gonna make 3 queries, and that's gonna give us the maximum in the whole red region. Okay? So like I said, this is gonna be the same. But now we're gonna have a segment, this segment tree of size C, right? The number of columns. We have one element for each column. We're gonna have the default. So this is gonna be a maximum. Yeah, I guess we don't need this. Yeah, so yeah, R1 vals. Well, how do we call this? Well, just call it our. Okay, so then we're gonna have our R2, which has to start from 1, right? Because it cannot be, so I have to leave space for R1. And then R3. And then I want to choose the, like I did before, right? I could even copy this. So here I have my column, the column of the second rook and the column of the third rook. And we want them to be different, right? And so and so now we're gonna have the current value. Okay, so the current value is going to be board of so this is the value of rook 2, rook 3, and now for rook 1 we're gonna do a query. Oh yeah, remember that here we have to first update, right? So we're adding a new row, right? R2 minus 1, right? So here we want to set at column C the maximum between the board at this row and this column and the value that it already had, right? So here we can use this. We can do a query of the range C and C, which is effectively giving us the value at C. And so now we have updated our segment tree. And so here we're going to query it. We want the maximum of this. But yeah, we need to know which is the minimum and the maximum of C2 and C3 and C2 and C3. Okay, so we want the range from 0 to the minimum minus 1, right? Then the minimum plus 1 and the maximum minus 1, and then the third region is going to be the maximum plus 1 and C minus 1, right? So those are the three ranges that I care about. Notice that in some cases this ranges will be empty, but that's okay. It's gonna return minus infinity in those cases, which is what we expect. Let's see if it passes, because I had, so during the contest, I had a solution that it was a slightly less efficient and it didn't pass. It's not passing now, so this passed. Oh, it's, let me do, so instead of doing the query for getting a value, let's have a special method just as a small optimization, because I think this passed a moment ago. So maybe it's flaky. Okay, it passed. I guess. Yeah, I don't buy that this is making such a difference. Maybe it was just. Let me retry the previous code. It might be flaky because this is not executed that's the that many times, and the optimization is very small, so I don't buy that makes a difference. But maybe it does. Maybe it does. No, it doesn't. Okay, so it seems like it's flaky. So I think this is bad problem setting from LeetCode. That, I mean, you either accept this solution or you don't. I think it's pretty the constant factor of these solutions looks normal. Yeah, I don't know what code they use to test a Python solution, but yeah, if you know a more efficient solution, you think it should have been 1,000 instead of. No. So I don't know another solution. What I don't like is that the if there is a more efficient solution, then you should make the constraints bigger so that this one doesn't pass. If the other one is the expected, or if this is if this is expected to pass, then make it 400 instead of 500, so that it passes clearly. Because what happened during the contest was that this solution didn't pass because of some details, some slight because I wasn't doing some of the optimizations here, but in C++ it passed without any issues. So I think it should have been like 400, not more, not 500. But if you know of a more efficient solution, let me know. I'm interested. I did not look into solutions from other participants, so I usually like to think about Python things. I try to think about the problems on my own and give you the explanations that I find. Anyway, so okay, so this is all. It's been 50 minutes, so I think that's enough for this contest. So thank you a lot for your support, and see you on the next one. Bye bye.